If you don't know me, I'm a postdoc here in the 6th floor of Stata, and I'm studying for the node today. My name's over there also. So today we're going to talk about garbled circuits. So I think last week we started doing a GMW protocol, right? Two-party computation or multi-party computation. Is that correct? So I think maybe you didn't finish the proof, but today we're going to do a short recap about what is two-party computation, and we're going to talk about an alternative approach for constructing these protocols based on this wonderful notion of garbled circuits. And yeah, that's it. So I'm going to start with a very quick recap. So what we're going to cover today, we don't need to cover a lot of material, but the construction of these garbled circuits can be a little tricky. There's a lot of kind of notations and indexes to count. So if at any point, it gets too much, or you don't follow what I'm saying, or you just need a second to think, you don't even need to ask a question. Just raise your hand or say my name, and I'll just stop or go a little bit slower, and you can take your time with the slides. Of course, I'll make these slides available for you later. So that's it. Okay, so let's get started with a quick recap of two-party computation. So in a two-party computation protocol, we have two parties, A and B. Every one of them has their private inputs, A and B. And their goal is to compute some joint function of their inputs, but without revealing too much or any unnecessary information about their inputs. So they start communicating according to some two-party protocol, and in the end of this protocol, they should learn the output of the function f. But ideally, they shouldn't learn anything about the other party's inputs other than what they can learn based on the output of this context. So when we want to define security formally, there's several ways to do this. But today, and also in the previous lecture, we talked about SemiHonest security. So what does SemiHonest security mean? It means that we assume that these parties are not malicious. They're actually following the prescribed protocol as it's written. Okay? If the protocol says flip a coin, they flip a coin. If the protocol says sends to the other party what the coin says, you send exactly what the coin said. You never lie. You never bias the coin. And the only thing the adversaries are actually trying to do is to look at the transcript of this protocol, look at all the messages that are being exchanged, and trying to deduce maybe more information. The protocol is only instructing them to compute this function f, but think about an adversary that after it's done interacting with the protocol honestly, it stops, it looks at everything that it saw during the execution, and it's trying to now learn as much information as it can, but it's kind of post-mortem. It's not, it cannot change its behavior during the protocol. So you'll see today that this is kind of, it feels very weak. Kind of during the protocol, we'll tell the adversary to behave nicely, and the adversary will behave nicely. It feels a little weird, but we'll see that it's okay. In the next slide, I'll kind of justify this. So if you have any questions, like you feel like this protocol is wrong, something like this protocol should not be secure, the first thing you should think, you should try to figure out is whether this problem is just a problem of a malicious adversary or a semi-honest adversary. Maybe if the adversary is semi-honest, this is not really a problem. So, so this is about semi-honest. What does this definition actually says? It says that there exists a pair of simulators, okay, such that these conditions hold. So let's parse what's written here. So the view of so this arrows denote the interaction between party A on input small a and party B on input small b. This is just a random variable that describes the interaction of this protocol where the parties have random coins and this specific inputs. And the view of A is just referring to all the information that A sees during this interaction. So the view of A includes, so you should think about it that the view of A should include all the information you need to reconstruct the execution of A exactly. So it includes the code of this party A, which is specified by the protocol. This party is completely honest. The code of the party, the input A, the randomness that this party takes, all the random coins that it flips, and all the incoming messages from party B. So if you have all the incoming messages and the randomness and the input and the code, you can actually compute all the messages that this party sends and even the final output that this adversary produces, that this party produces. So this is what the view consists of. So we want to say that everything the adversary sees can be simulated by this simulator SA, given only the input of the party, which is obviously available to the party, and the output of the function, which has to be available to the party. We want this party to learn the output. So given only this two minimal pieces of information, the adversary we can simulate everything that the adversary sees during the protocol. This means that the protocol does not reveal any more information than what the simulator can compute from these two pieces of from this input and output. Okay, does that make sense? Question about this. So the second row is just analogous from the other side. Party B cannot learn more than what can be simulated from the input and output. Any questions about this? So in this definition, what happens is that these parties are kind of honest, and the adversary, where's the adversary in this definition? The adversary is the distinguisher that tries to distinguish between this benign execution and this honest execution. So this is this post-mortem adversary that kind of looks at what happened in the protocol, looks at the view, and tries to learn information, tries to distinguish between this execution, between this simulated execution, which is completely free of leakage, and this real execution. So really the adversary here is what tries to distinguish between these two distributions. Everyone else is honest. Okay. So I mentioned this, the semi-honest definition feels very weak. Why is this okay to consider semi-honest instead of full malicious security where the adversary can do whatever it wants? In real life, the adversary can do whatever it wants. So the reason is that if you have a two-party computation protocol or a multi-party computation protocol that I didn't discuss, but you can generalize this notion to multi-parties, if you have a protocol with security against semi-honest adversaries, you can generically transform it into an adversary with full-fledged security against malicious adversaries. And there's even a nice compiler here. You just give it a protocol of this type and it produces a different protocol that has this notion of security. This compiler is strongly using these tools that we discussed in previous lectures, zero-knowledge proofs for NP and bit commitments. And this is going to be the subject of next week's talk, especially the Wednesday talk next week. So this slide is just supposed to make you feel comfortable with the fact that we're only going to cover semi-honest security. So this wonderful GMW theorem says that for any, that if we have this tool called obliviousTransfer, it's a two-party protocol with semi-honest security, we can turn it into a two-party protocol that computes any function f. In fact, we can even get a protocol for multi-parties. So did you talk about GMW for two parties or for multi-party? Do you remember? Two parties? Okay, did you mention anything about extending this protocol for multi-party? Okay, so this is an exercise. It's actually not hard to see that whatever you did for two parties works pretty easy for more parties, for three parties and more. You just share the bits of every wire between more parties. And I think you're going to need to do this in the problem set probably, I'm not sure. But today we're going to focus on the two-party setting. So what is this oblivious transfer? You can just think about it as another protocol, two-party protocol, but not for an arbitrary function f, just for a very specific function, kind of a simple, trivial, minimal function, not trivial, but minimal. So we call one party the sender and one party the receiver. So this is a drawing for oblivious transfer. The sender has two strings, A0 and A1, and the receiver has a bit, B. The receiver wants to get one of these strings according to the bit, and that's the output of the receiver. The output of the sender is just nothing. The sender learns nothing. In particular, it does not learn the input B that the receiver wants to choose. And before we talked about protocols that have the same output for both parties, but you can easily generalize this to every party outputs their own function. And supposedly, in the previous lectures, you constructed such a protocol from Tracker permutations, maybe, or something like this. So I'm not going to talk about how to construct this obliviousTransfer, but in our construction, I'm assuming that we have such a protocol with semi-honest security. So we're good on the notion of obliviousTransfer. What does it mean? So the sender has like a database of 2 entries, 2 bits, and the receiver wants to learn one of these strings, but it doesn't want the sender to learn which one of these strings it's querying. Okay. And it doesn't learn anything about the other string that it didn't ask you to see. Okay, so just in terms of what you saw the previous time, the GMW protocol, it gives us a protocol where the number of rounds in the protocol kind of grows with the complexity of the function that you're trying to compute. So for every wire in the circuit, you're kind of communicating one round. You can even kind of try and optimize this and get the complexity to depend only on the depth of the function. So if you think about the function as computed by a circuit, you can take all the wires in the same level. You can divide the circuit into levels, and all the wires that are in the same level, you can interact in parallel. So you don't need to spend more rounds for every wire. But between different layers, you have to interact in more and more rounds. So the round complexity of the GMW protocol grows with the depth of the circuit computing the function. In terms of the number of parties, you saw the two-party version, but it easily generalizes to multi-party. What we're going to do today is talk about an alternative protocol based on garbled circuits. And the main advantage of this protocol is that it gives us a constant number of rounds that doesn't grow with the complexity of the function. The communication in these rounds, the length of the messages will grow with the complexity of the function, but the number of rounds will not. The disadvantage of this protocol is that it's kind of tailored to two parties. It's not at all clear how to generalize it to 3 parties or more. Now, what you can do, and what you will do in the problem set, is try to combine these two protocols together to get kind of the best of both worlds. So you can use techniques from garbled circuits and GMW to construct one protocol that has constant number of rounds and supports multi-party. And I think this is a question in the homework, I'm not sure. So this is, the plan for today is just to cover this. And this garbled circuit techniques, beyond the fact that it gives us protocols with constant number of rounds, it turns out that it has many other applications that are kind of well beyond the scope of two-party computation. And if you look at the actual applications of garbled circuits, it's kind of surprising. It's things that have nothing to do with secure computation, and it's kind of all over the place in crypto. So this tool of garbled circuits, beyond the fact that it has a really cool name, you can go home and say, I know how to garble circuits. It also has a really strong application and is very diverse. So here is a fantastic theorem by Yao. Assuming that you have a constant round oblivious transfer protocol, there's also a constant round two-party computation protocol for every function f. So question about the statement or the theorem that we're trying to prove today. About the motivation. Okay. So I'm going to start by kind of putting aside this notion of secure computation, and we'll try to construct this simpler object called a circuit garbling scheme. Right? So I'll tell you, in the slide, I'll tell you what is a circuit garbling scheme. And once I define what it is, we'll see how circuit garbling schemes are useful to construct two-party computation protocols. So in a circuit garbling scheme, you have this encoding algorithm, C encode, that takes a description of a circuit C, and it outputs kind of an encoded or a garbled or an encrypted version of the circuit that we denote by C tilde. Okay? And this encoding has a secret key. For now, you can think about the secret key as just a random string that is not known to anyone except the encoding algorithm. We also want to take an input x to the circuit and garble the input as well. So we have an input encoding algorithm that takes the same secret key. It's important that both of these algorithms take the same secret key. It takes any possible inputs to the circuit and produces a garbled or encoded version of this input. So now that you have the garbled circuit and the garbled input, the natural thing to do is to combine them together. So we always also have a way to decode this garbled circuit and garbled input together and learn the evaluated value, the value of the circuit evaluated on this input. Okay? So you can kind of evaluate the garbled circuit on the garbled input. But what's important is that that's the only thing you can do. So if you have this garbled circuit and garbled input, you should not learn anything else about C and about X except the fact that this is really the evaluation of C of X. So the main thing that we want to hide is X. We assume that the original circuit C is kind of public. We're not trying to hide it. We are trying to hide the input, and we're also trying to hide all the intermediate wires in the computation of C of X. So not only you don't learn the input, you don't learn any kind of intermediate step in the computation of the circuit. The only thing you learn is the last bit of the computation, which tells you if the circuit outputs 0 or 1 on X. So another thing that is important to notice here is that even though the encoding of the circuit and the input, they share the same secret key, there are different algorithms. This algorithm only sees the circuit. This algorithm only sees the input. Okay? There's not one algorithm that sees the circuit and the input and produces these encoded values. And that's going to be important, in fact. So here's a question. Let's say that I only wanted you to build one algorithm that takes both C and X and produces these garbled circuit and inputs such that you can decode, but you cannot learn anything else other than the output. I'm claiming that it's very easy to construct such a garbling scheme if you only need to construct one algorithm that gets both the circuit and the input. How do you do it?
Use the bit.
Exactly. If you have one algorithm that sees both the circuit and the input, it can just evaluate the circuit on the input, learn the output, and now the encodings are just the output. So basically what you're trying to encode is not the circuit or the input, you're trying to encode the output of the computation. If you knew the output of the computation, it's very easy to encode. You just output it in the clear. You forget about all the inputs. But the problem is that none of these algorithms actually can run the computation. This algorithm only has the circuit, this algorithm only has the input. So none of these algorithms can compute everything on its own. The decoding algorithm is going to be the algorithm that actually does the computation. But it does this in an encrypted form, so it cannot learn the input and the intermediate values, just the output. So how do we formalize this? We again use the simulation paradigm that we see over and over again. This is our way to capture this statements that there is no knowledge is revealed beyond something. Whenever we see such a statement, we formalize this using a simulator. So there exists an efficient simulator, S-garble, such that if you pick a random secret key, for every circuit and input, if you pick a random secret key and you look at these garbled circuit and garbled input that are produced from these algorithms, this distribution can completely be simulated given only the description of the circuit, we're not trying to hide the circuit, and the output of the circuit on X. So we're not trying to hide the output, we want to be able to learn the output. But if you only have these two pieces of information, you can actually generate a garbled circuit and a garbled input that look completely identical to the real garbled circuit and garbled input, even though you have no idea what the input is. You have no idea what's the actual computation, but you can produce this garbled circuit and garbled input or something that looks indistinguishable from them, given only the output. So is this syntax okay? Okay, so we're going to ask for one more property from our garbling scheme. We want it to be decomposable. So before we mentioned that you garble the circuit and the input separately. Now I want to take this even further. I want to garble every bit of the input separately. So no single algorithm gets the entire input. There is one algorithm, encode 1, that gets the first bit of the input, and it produces the garbling. And there is a similar algorithm for every individual bit of the input. Okay, so you don't have to see the entire input. You just see one input of the one bit of the input, and it produces a garbling. And now the decoding algorithm takes all of these garblings, the garbling of the circuit and all of the individual inputs, and it gives you the answer. And notice that even though this input is a bit, the garbled input doesn't have to be a bit. It can be a long string that depends on the secret key. This is okay for us. Okay, so this is the notion of a garbling scheme. Any questions about this? So now I'll show you how to take, in the first part of the talk, I'll show you how to take a circuit garbling scheme together with an obliviousTransfer protocol and construct SemiHonest secure two-party computation and construct a constant round secure computation protocol. I'm not going to show you how to construct this circuit garbling scheme yet. You have to believe me that it exists. In the second part of the lecture, I'll actually construct this circuit garbling scheme, and this will be more involved in terms of the details. So let's get started. So we want to construct a two-party computation protocol. We have two parties, A and B. Their inputs are X and Y now. And they want to compute the circuit C evaluated on both X and Y. Okay, so the circuit takes two strings, x and y. So C is our function. Okay, and the tools that we have at our disposal are a circuit garbling scheme and oblivious transfer protocol. So party A is going to start. It's going to sample a secret key for the garbling scheme, and it's going to garble the circuit, and it's going to garble every bit of its input separately. Okay, so that's kind of the natural thing to do, I think. So now it has the garbled circuit, it has the garbled input, but the X inputs are just half of the inputs to the circuit. The circuit also wants a Y input. And we would let the party A garble the input Y, but A doesn't know the input Y. This is the entire goal in this protocol. We want to compute this function, but none of the parties know the other party's input. So what is that? So what is the party A going to do because it doesn't know the input Y? Anybody has any idea? How is it going to garble the input Y? So the idea is that we're going to garble all the possibilities for the input Y. So first of all, we're going to send, in the first message, we'll send the garbled circuit and all the inputs that we do know how to garble, all the X inputs, to B. And again, these circuits should not reveal any information about X, so it's okay to send them. So now we're going to garble all the possibilities for Y. So for every possible index into every possible position of the input, n plus I, so I goes over all the bits of Y, and the bits of Y, the locations of these bits are n plus I, right? Because Y is the second input. And we're going to garble both the input 0 and the input 1. We don't know what's the actual bit in location I of Y. It's either 0 or 1. We're going to garble both of them. So the garbling of the bit 0 in location I will be Y I0, and we also have Y I1. So we have both of these options, and we're going to send them to B, but we don't want to send all of these garbled inputs to B. We're only going to send the garbled inputs that B actually needs to run the computation, and this will be important for security. So how do we know which of these garbled inputs the B needs? We're going to use an oblivious transfer protocol. We're going to construct this tiny database that consists of Y0 and Y1 for every I. And for every I, we're going to run an oblivious transfer protocol. Party B is the receiver. It chooses which one of these strings it wants, the string that corresponds to Yi. And the output of this protocol for the receiver is just the garbling of the correct input, right? The sender doesn't get any output. It just puts in the two possible garblings. And the output of B is the correct garbling that corresponds to its input. Okay? So this is how we garble the input of party B. We garble all the possible inputs, and then party B chooses one out of two garblings for every input bits. And now B has the correct garbling of the input and nothing more. Is that okay? So now what does party B has? It has the garbling of all the Y inputs, it has the garbling of all the X inputs, and it has the garbling of the circuit. So the last step of the protocol is kind of straightforward. Just take all these garbling and decode the output of the circuit. Okay, so from all these garbling, you can actually evaluate a C on X and Y, and you can send this output back to A. Of course, these parties don't trust each other. How does party A trust party B to send the right output? Maybe party B sends a different output. It wants to make A get the wrong output. How do we prevent this from happening? So the answer is that there's many ways to do it. The answer is that we don't do it because we're only interested in SemiHonest security. So these parties are completely honest. B is following the protocol. The protocol says send the correct value. It sends the correct value. Okay? After the execution of the protocol, we have an adversary that looks at this execution and tries to learn more. But it's not like party B is actually trying to maliciously make party A fail. So it turns out that getting this weak notion of security is enough. We can actually generically make sure that B is behaving correctly also in real time. But we're not going to do this today. So the steps of the protocol, again, you garble the circuit, you garble the part of the input that belongs to you, you garble all the possibilities for the input that belong to the other guy, and then you communicate the right garblings, the garblings of the right inputs using oblivious transfer. Once the other party has all the garblings and all the inputs in the circuit, the other party can decode the output and send it to you. So the next thing that I'll show you is how to prove that this protocol is really secure. So I'm going to give you a simulator for both sides of this, a simulator for the view of A and a simulator for the view of B. I'm not going to write them extremely formally. I'll just tell you what's the component of the simulator and filling out the details of the simulator and actually prove that the simulation, the view that the simulator produces is indistinguishable from the view of the party in the actual protocol. This I will leave for you as an exercise, and it's actually a really useful exercise to make sure that you understand this protocol and also the definition of two-party computation, and also the simulation paradigm in general. So this is a great way to exercise these ideas. So I'll just sketch the simulators to help us, to help you kind of get started. So the simulator, remember, the simulator for A needs to create the entire view of party A, but it only knows the input, x, and the output of the computation, which is c of x, y. The most important information that this party is missing is y. Right? If it knew the string y, it could simulate the entire interaction, both sides. But the simulator doesn't know y. It only knows the output of the computation. And still, it needs to produce messages coming from party B that looks like they were sent by a party that actually has the right value of y. So let's try and do that. So in our protocol, party A starts. So it's really easy to simulate this part. You just run the same code that party A would run. You create a garbling of the circuit and the inputs that you know, and you send them over. Okay. Now the next message is the oblivious transfer message. And in the oblivious transfer message, that actually depends on the bits of y. The receiver chooses which bits it wants to receive, and we don't know these bits. We don't know why. So in here we're going to create these labels, but in order to simulate the oblivious transfer messages, we're going to use the security of the oblivious transfer protocol. So party A is not supposed to learn the bits of y, which means that all the messages that it sees actually hide these bits. In fact, you can generate something that looks indistinguishable from the messages of the OT using the simulator of the OT protocol. This is exactly where we use the security of the OT. We use the fact that party A doesn't learn the bits of y. Okay. So you can just run the simulator of this oblivious transfer sender. So what is written here, for every one of the parallel executions, for every I, we simulate the view of the sender, the input, and we give the simulator input to the sender. The sender inputs to the oblivious transfer protocol is just these two strings. And we also give it the output of the oblivious transfer protocol, which is nothing. So we don't give it at any point any information about y. We don't need the actual bit yi to simulate the view of the sender. So this is how we simulate all the oblivious transfer messages, just this side of party A. And now we need to simulate the last message where party B sends the output. Great, we know the output, right? So we just send the output. Okay? It's not like this output was really computed from the garbling using, there wasn't actual computation of the garbled circuit. We just simulate this side of the protocol. So intuitively, what the simulator says is that in this protocol, the adversary, the party A doesn't learn anything except what it learned from the oblivious transfer, which is nothing, and the output of the protocol, which is sent to it in the last message. This is kind of the intuitive statement that is formally proven by writing down the simulator. Okay, so this is kind of the easier side of the simulation, because party A really learns nothing. It just garbles things. The interesting part of the simulation is actually the other side. Party B is the party that actually gets the garbling. And in order to prove security for this party, that this party doesn't learn too much, we're actually going to use the fact that the garbling scheme is secure. So we're going to start to simulate the view of this party. We'll start by doing what the party. So the simulator doesn't have the input x, it only has the input y and the output of the computation. We'll start by producing the garbling. We can't garble the circuit because we don't have the input, we don't know x. But we'll produce simulated garbling, things that look good. So we know the output of the computation. We know what this garbled circuit is supposed to produce. So we'll just create a garbled circuit and garbled inputs for x and for y that look good by using the output of the computation. This is exactly what the simulator of the garbled circuit is giving us. It gives us garbled inputs and garbled circuit that look like they're going to produce the right output. Okay? And we're going to interact with party B based on this garbling. We're going to use the simulated garbling as if there were the correct garbling. We don't need to know x to produce these garblings. Is that point clear? Some nods. Okay, feel free to ask me questions, because this is really, you need to have some experience with simulation before you can feel comfortable with this type of protocol. You can ask me here, or you can just work out the details afterwards. Okay, so we send the first message, which contains the garbled X inputs and the garbled circuit. Now we have the input Y, so we can kind of simulate all the messages in the OT protocol by simulating the side of the receiver. So to simulate the side of the receiver, we just need to know the output of the receiver. So we don't need to know both the garbling of Y0 and Y1. We just need to know the garbling of Y that the receiver actually gets. And we know that. This is exactly this simulated garbling that we created. So we simulate the side of the receiver. This is the input to the receiver, the bits that it wants to see. And this is the output. Okay? We don't know kind of the other string of the oblivious transfer. We never generated it. But we only need to know the output of the oblivious transfer. So now party B has the simulated garbled circuit and the simulated inputs, and it will try to decode, and it will produce this output. And by the correctness of the simulation, this output will be correct. So again, what the simulator is telling us is that all the view of party B consists of a garbled circuit and garbled inputs for X and Y, and therefore the simulated party B doesn't learn anything from this garbling except the output. And this is exactly captured by the security of the garbling simulator. This is exactly what the garbling simulator guarantees for us. So again, work out the details, prove that the simulation is indistinguishable from the real view. You'll need to use both the definition of the garbling simulator and the OT simulator, and that's the exercise. So some more exercises. So we talked about this one. Write down the simulators formally and prove that they're valid, prove that they're indistinguishable from the right execution. If you can do this, then you should feel pretty good about your understanding of the simulation paradigm and two-party computation, and also oblivious transfer and garbling. Another exercise is to kind of try and shrink this protocol down. So this protocol has a constant number of rounds, but we were kind of liberal with the rounds. Turns out that you can do something a bit more tight. So let's say that I give you an oblivious transfer protocol that only has 2 messages. Try to build a two-party computation protocol that has 3 messages. Try to kind of shrink down the number of rounds. And the second part of this exercise is to prove that both of these numbers are actually opposite. Any secure two-party computation protocol has to have at least 3 messages. So both of these protocols, 2-message oblivious transfer, 3-message 2PC, can be constructed based on kind of standard assumption, discrete log, and stuff like that. But in this exercise, I just want you to do this transformation. Assume you have this 2-message oblivious transfer and get the protocol that we just saw down to 3 messages. Okay, so this was the first part. I told you how to take a circuit garbling scheme together with oblivious transfer and to build a SemiHonest protocol for two-party computation. Now we're going to kind of open up this box, this circuit garbling box. I'll tell you how to encrypt a circuit, how to garble a circuit, how to garble an input, such that they really reveal no information except the output. It sounds kind of magical, but turns out you can do it. And we're only going to use a secret key encryption in order to do this. So you can build a secret key encryption based on any one-way function. So the assumptions you needed for oblivious transfer were something like Chopper permutation or maybe LWE. But the assumptions that we need to construct a circuit garbling scheme are kind of minimal, only one-way functions. So this is where the heavy lifting is actually happening. This is where all the interesting parts of the protocol are occurring. Okay, so let's get started. So we're going to think about our functions that we want to compute as circuits. This is why we call it circuit garbling. So what's a circuit? It's just a collection of gates and wires. For simplicity, I'm thinking about this as non-gates, but you can think about any type of gates. We're not going to use the fact that it's non-gates. You can garble any circuits with any type of gates. We're just assuming that these gates are binary. They have two input wires and one output wire, but the output wires can kind of fan out. So you can have one output wire that kind of use it as input to two other gates. Okay? Every wire can fan out as many times as you want. The size of the circuit needs to be polynomial. We assume that it has one output wire, and we call these the input wires. This is where we put the inputs to the circuit. We compute the circuit gate by gate until we get a value on the output wires. And the wires have names, 1, 2, 3, all the way to 12. Okay? The input wires are 1 through 6. The output wire is 12. So far, really standard stuff, right? So now we want to garble the circuit. So here is how the garbled circuit is going to look like. And now we just need to fill out the details. So the garbled circuit has the same layout as the original circuit, but all the gates are replaced with these special gates called garbled gates. Okay? These will actually be different. In the original circuit, these were all just the same copies of the same gate. Here, the garbled gates will be different for every location. Okay? And also on the wires, instead of just giving them names 1 through 12, we actually have some information associated with these wires. So for every wire, we choose two secret keys, two random secret keys. So we have one for every wire. We have one key that corresponds to the value 0, and one key that corresponds to the value 1. So for example, for wire number 1, we have K10 for 0 and K11 for the value 1. Here on the 9th wire, we have K90 for the value 0 and K91 for the value 1. So is that clear? It's just notation so far. You're not supposed to understand the meaning of these keys. Okay, so what is the meaning of these keys? So what does it mean that you have a key? It means that you have permission to do something. If you have a key to your house, it means that you have permission to go into your house. Okay? So if you have the key for wire 1, that associated with 0, this means that you have permission to execute the circuit with the first wire taking the value 0. Okay? And same for the intermediate wires. If you have K11.1, it means that you're able to evaluate the circuit where this intermediate wire takes the value 1. Okay? So the first property of the construction that we're going to try to achieve is that at any point, you never know, you can never learn two of the keys for the same wire. So for every one of these wires, when you evaluate the garbled circuit, when you decode, you will only learn one of these keys for every wire, and that's the key that corresponds to the correct value of the wire. If you actually evaluated the circuit on the input, you would get some value. So we want to make sure that for every wire, you get the correct key that gives you permission for the correct value. So we'll see how to enforce this. The first thing we need to make sure is that when we encode the input, the way we encode the input is by giving you permission to evaluate the circuit on the input. So if we want to encode, so remember we encode the circuit and the input separately. So this is the encoding of the circuit. How do we encode the input? We have this, let's say we have an input 0, 1, 1, 0, 1, 1. We just take every bit of the input and we encode it separately. So the first input is 0. Which means that you should have permission to execute the circuit with K10. Okay? The last input bit is 1, which means that for the last wire, we'll give you the key that corresponds to 1. So giving you these keys is just giving you permission to evaluate the circuit on this particular input. Is this okay? So now we need to design these garbled gates in a way that preserve our permission model. So specifically, I have, let's look at the first garbled gate. I have a permission for the first wire for 0, for the second wire for 1. And if you NAND 0 and 1, you get, what's the NAND of 0 and 1? Does everybody know what a NAND gate is? Okay. So NAND is just the negation of AND. I'm assuming you know this, you're just being quiet. So we have A and B, and so the AND of 0 and 0 is 0, so the not of negation of it is 1. And if you have two 1s, their AND is 1, so the negation is 0. So this is the truth table for NAND. It's very useful. Okay, so you have permissions for 0 and 1. And the NAND of 0 and 1 is 1. So you should get permission for K1, K7 1, but not K7 0. So the garbled gate is going to make sure that you get permissions for the right output keys. Okay? And this is true for every one of these garbled gates. And now once you have permissions for the right values for the wires in the second layer, you can use these keys to kind of get more keys in the next layer, and so on and so forth, until you get permissions for one key, and you get one key for the output label. So now the second key property of this construction is that at no point during the evaluation, you get these keys. Every key corresponds to either 0 or 1. But this semantics is kind of only in our heads. As someone that evaluates the garbled circuits, you never know if your key is a 0 key or a 1 key. So these keys are both random strings. You have one of them, you don't have the other. You have no idea if this is the 0 key or the 1 key. It's just a key. And at no point, we're never going to tell you which key you have. So you can distinguish between the situation where you have the 0 key of some wire and the 1 key for some wire until the very end. Okay, so we don't want you to learn the intermediate values in the evaluation of the circuit. This is exactly the security of the garbling, but we do want you to learn the output. So now you have this key, K12.1. How are you going to know that this is the 1 key and not the 0 key? So we have to tell you that. So we're going to include in this garbling also something called an output translation table. It just says if you get a key 12.1, this is the 1 key. And if you get key 12.0, this is actually the 0 key. And we're going to write this explicitly. But we're not going to give you a translation table for any of the previous wires. We're actually going to prove that for none of these keys that you get along the way, you don't know if it's the 0 key or the 1 key. This is where the security of this garbling scheme is going to come from. So these are the two key properties that you need to remember. When you evaluate a garbled circuit, you learn one of two keys for every wire. It kind of corresponds to the correct value. And you don't know what is the correct value until you reach the output wire. Okay, good. So the next thing I need to show, so you already know how to garble the input. The main thing that I need to show you is how to garble these gates. So let's see how a garbled gate looks like. So this is the first garbled gate. It takes wire 1 and 2 and outputs wire 7. And we want this garbled gate to have the following semantics. If we give it the two 0 labels, it produces the 1 label. And same for every other possibility. But if we give it the two 1 labels, it gives you the 0 label. So how are we going to build this gate? And remember, if you don't have these right keys, you're not supposed to get, unless you know both key 1 and key 1.1 and K1.2, you're not supposed to learn K07. Okay, any other combinations of input is supposed to give you K1 for the output. So the only situation where you have permissions for this key is if you know both of these keys. So we can't just give you both of these keys in the clear. We want to make sure that you only get the keys that you're supposed to get. So how do we make sure that you can only learn a key if you have another key? Does someone have an idea how to do that?
Use the two input keys to encrypt the output key.
Encryption, great. In the physical world, we would just take key 7 and put it in a box and lock the box with key 1. And that makes sure that you need key 1. And we're also going to put this box inside another box that has a lock that opens under key K2. And only if you have both of these keys, you can open both of these boxes and get the key. Okay? This is like when you launch a nuclear weapon, you need two keys to open whatever. So the analog, so we're going to create these pair of double boxes. We're going to implement them using encryption, and we're going to create one of these boxes, double boxes, for every possibility of every possible behavior of this gate. So for every combination of two inputs and outputs, we're going to create this box. And now, if you have two input keys, you can just try and open one of these double boxes. And I'm claiming that you're only going to succeed in opening one of these double boxes, right? Because unless you have exactly these two keys, you cannot open this one. Okay, so for every one of the other boxes, you're going to miss at least one of the keys, and you're not going to be able to get to the 7 key underneath. So is that relatively clear? Okay, so this is how we're actually implementing it, no box. We're just going to use, instead of a box inside a box, an encryption inside of an encryption. We encrypt the output wire under both input wires that you have. Okay, if you have this key and this key, you can learn this key. If you have this and this, you can learn this one. Okay, this is exactly the semantics that we want. Okay, so so the last thing that we want to do is we want to make sure that you never know which key you have. You never know if you have the 0 key or the 1 key. And if we just order these encryptions in this canonical ordering, you always know that the third row corresponds to the 1 key for the first input and the 0 key for the last input. And the order of the rows tells us the semantics of the input, if it's a 1 key or 0 key. So we're also going to shuffle these rows. Okay, we're going to give you all of these for double encryptions, but we're going to give it to you in a random order. So now you have no idea if this third row corresponds to this configuration or this configuration. You don't. So this is a good idea for security, but it introduces some difficulties. Now I want to evaluate the garbled circuit. What do? I need to, let's say I have this key and this key. I don't know that I need to go to the third row and try to open both encryptions. I actually need to try all these double encryptions, all these double boxes, until I see one of them that actually opens. Okay? So the algorithm is that you have two keys for the input wires. You just try to open every one of these encryptions, and if both encryptions open, you know that you have the output, the key of the output. So is this evaluation mechanism clear? Good. So eventually the garbled gate will just consist of these 4 double encryptions in a random order. This is just one gate of the circuit. It's kind of tailored to K1, K2, and K7. For every other gate in the circuit, we'll need to create new encryptions. So there's a tiny bug with what we just said. What I told you, the algorithm that I told you involves trying all of these encryptions and seeing which one of them is open. But if you think about encryption scheme that you already saw in this course, for example, encryption scheme from El Gamal, not every encryption scheme tells you if you're using the wrong key. So we know that if you don't have the right key, you shouldn't be able to decrypt correctly. But it could be that you're trying to decrypt with the wrong key, and you're just getting something that looks like a correct decryption, but it gives you like the wrong value or something like this. So every key that you try to decrypt, it will give you a bad value. This is an annoying behavior that doesn't happen if you have a locked box, a physical locked box. If you have a physical locked box and you use the wrong key, then you know you're using the wrong key. It doesn't turn. It's not like the box is going to open and you're going to find like a completely different thing inside if you're using the wrong key, right? So we want to build this encryption scheme that really behaves like a box. If you try to open it with the wrong key, it doesn't open. It's not like it's opening to a different value. So we call this an encryption with wrong key detection. And the property that we want is that if you sample 2 keys for the encryption scheme, 2 encryption keys, and you try to encrypt with one and decrypt with the other, almost with probability 1, you're going to get an error, the value bottom. Okay, so this is not a lot to ask. Turns out that you can take any symmetric encryption scheme and turn it into a new encryption scheme that actually have this property of wrong key detection. And I'm not going to go into the details, but it's really simple. You can do it in many different ways. One way you can do it is just add some random tag to your secret key. Use the second part of the secret key to actually encrypt, and just include this random tag in the clear inside your ciphertext. When you decrypt using this random tag, and you get a ciphertext, make sure that the tag inside the ciphertext is equal to the tag inside your key. And if you're using two different keys, these tags are not going to match. You're going to get an error. Okay, this is completely straightforward. You can make sure that this works, or you can come up with a different way to do it on your own. It's completely fine. Okay, so this was kind of a tangent. What we actually want to do is, what I want to do now is kind of connect all these pieces together and tell you how do we garble the circuit, how do we garble the input. So again, we have this garbled circuit. For every wire, we create two keys, for 0 and for 1, but we never tell you the keys. We never include them, not with the garbled circuit, not with the garbled inputs. We only include some of them. So when we garbled some input, we only give the keys that correspond to the input wires, and they correspond to the right values that we want to garble. And we also give you, when we garble the circuit, we give you a collection of garbled gates. Okay, so in the picture here, there are no indices. I just write k every time, but actually these k's are different for every gate and for every row in every gate. So we construct these tables that actually map the correct keys for the input wires to the correct keys of the output wires, and we do this for every gate in the circuit. So when we garble the circuit, we create this garbled table for every gate, and we also give you this output translation map, how to interpret the semantics of the output keys. So this output key goes to 0, this output key goes to 1. So this is how you garble the circuit, this is how you garble the input. How do you decode? How do you decode this garbling? If you have the garbling of the circuit and the garble of the input, you should be able to compute the output. So this will be kind of a review of the construction. So the first thing that you do is you take all the keys for the input and you write them on the input wires. So now for every gate in the first layer, you take the two keys that you have and you try to decrypt every row in this gate. 3 of these rows are going to fail, either in the first encryption or the second encryption. One of these rows, both encryptions are going to open, and you're going to get a new key. You write this new key on the output wire, and you repeat in the second layer. Now you go take these two input wires and try to get this one. Eventually you get the key for the output label. So even though when we generated these circuits, we had 2 keys for every label, when you evaluate the circuit, you only see 1 key for every label. And note that you have no idea if this is the 0 key or the 1 key, right? If you look at the superscripts, you know, but when you actually evaluate the circuit, you don't have superscripts, you just have a random string. Okay, so you have no idea if it's coming from the 1 key or the 0 key, until you reach the very end. And here you get this random key. You can you can see which one of these keys it is. You can see that it's the 1 key, and now you know that the circuit outputs 1. But other than that, you didn't learn anything. You just see a sequence of random keys. So this is how you evaluate the garbled circuit. So the next thing that we're going to do is talk about security, but does anybody, this would be a good time to kind of stop and maybe try to figure out questions about the construction, about the evaluation process of this circuit. Kind of run this evaluation process in your head, see that you understand how to generate all these garbling gates and wires and labels. So here's a question. So when we garble the circuit, we need to choose 2 keys for every wire. And when we garble the input, we need to give one of these keys. But these are 2 separate algorithms, right? How do we know in this algorithm to give out the same key that we used to garble the first gate, right? These are completely separate algorithms. How can they both output the same random key? I kind of assumed that it's okay. I wrote all the keys on the board, but why is this okay? How can the encoding of the circuit and encoding of the input share information about the keys? Any ideas? So remember, both of the encoding of the circuit and the encoding of the input, they both use this secret key. Okay? What are they actually using the secret key for? To generate all these other random keys. So the first thing that you do in these algorithms is you take your secret key, you think about it as a seed of a pseudorandom generator or a pseudorandom function, and you kind of use it to, you expand it. You use it to generate a very long random string, and you break this random string into many blocks, and every one of these blocks is one of your keys. So using this one secret key that you coordinate, you can generate many secret keys, and you generate the same secret keys here and here, and you just call them K10, K11, and so on. So most of these algorithms can coordinate the randomness, but they don't know, in this algorithm, you don't know what's the garbling, what's the circuit that you're garbling. Here, you don't know what's the input that you're garbling. Okay, but you have the same access to the same randomness. So this is how you use the secret key. Okay. Any more questions about the garbling process? Great. So now, in the last part of this lecture, we're going to do the proof. The proof is by demonstrating a simulator for this garbling scheme and showing that it's a good simulator. And I'm going to warn, yeah, question.
So the person, when they put the input, gets the output of like K10, K21 in this example, right?
Uh-huh.
So then, so he could do this multiple times, right? So he could, so he gets to see like what when he goes to the top one there, like what the output he gets out. So he could try couldn't you try various different values and see like which one is the same and which one doesn't, and then
Okay.
sort of deduce the.
Fantastic question. Thank you. Okay. So here is the question as I understood it, and please correct me if I'm wrong. But the question I understood is great, so I'm going to answer that one first. So this algorithm, you can use it to encode any input that you want, right? What happens if you kind of encode many inputs, and you kind of get a bunch of labels? You know, in one input the first bit is 0, in another input the first bit is 1. You get K0, K1. Eventually you get all the keys, right? You kind of start using these keys to open these gates. You see which encryption is open, and you have many keys. So in one time this encryption will open, one time this encryption will open. Eventually you're going to get all the keys here. Okay? This is very bad. First of all, you get both keys for every wire. We said that this is a bad idea. And secondly, once you open all of these encryptions, you can see which output key appears once and which output key appears 3 times. The output key that appears 3 times is the 1 key. Right? This is how NAND works. The output key that appears once is the 0 key, so you also learn which key is 0, which key is 1. So what do we learn from this exercise? We learned that if you can evaluate the same garbled circuit on many garbled inputs, then all security is lost. We only have security if you get one garbled circuit and one garbled input. Permission only for one input. Okay? Once I give you 2 garbled inputs that are different, I'm guaranteeing nothing about security. It's not that if I give you one garbled input, you can learn the output of the circuit on this input. If I give you another garbled input, you can learn another output. If I give you 2 garbled inputs, you can learn the 2 garbled outputs, but you can learn much more. And this will actually be a problem in our construction. We're only going to use this with 1 garbled input. Okay? So remember, if you go back to the protocol, what party A sends to party B is a garbled circuit, and 1 garbling of every input. This is why we never want to send party B Y0 and Y1. We don't know why, right? So we create garbling for both labels, both values, but we only send one of them to Y. Why don't we send 2? Because then B is going to learn both keys for the same wire. This is why we use obliviousTransfer, to make sure that we only send one label for every wire. So just to clarify, we're going to, in our security proof, we're only going to consider a situation where the distinguisher gets to see 1 garbled input and 1 garbled circuit, never 2 inputs for the same circuit. Okay? And encoding the input is something that the distinguisher cannot do on its own. You have to have the secret key. You have to have access to all the keys in order to garble an input. Okay? Once I give you a garbled input, you can use it, but you cannot generate another garbled input unless I give you another one. And I will never do that. Does this answer your question? Great. Thank you. Okay. So what's going to happen in the simulation? We're going to... so first of all, the simulation will have a lot of indices. It's going to be kind of confusing. You're going to have to stare at it after class or something like this. But don't let all this formalism confuse you. The simulation is actually extremely simple. What is the argument here? So let's maybe just flash this. So we want to simulate a garbled circuit and a garbled input, given only the output of the circuit. What's the intuition? This is basically saying that if I give you a garbled circuit and a garbled input, you don't learn anything other than just decoding and learning the output. What do you learn from a garbled circuit and a garbled input? So you're basically learning some keys for the input. You can use them to learn more keys for the intermediate wires, and you learn more and more keys. But you just see random keys. You don't know if it's 0 keys or 1 key. So it's just like a process where you learn one random key for every wire. And in the end, you get one random key, and you actually know if this is the 0 key or the 1 key. So this shouldn't tell you anything other than the output. And this is exactly what our simulator is going to do. It says, OK, I want to generate a garbled circuit that produces this specific output. The output, let's say, 1. So I'm going to just generate a garbled circuit. I have no idea what's the input. I'm just going to give you one key for the input. I don't know if it's a key for 0, a key for just a random key for every input wire. And you're going to, and the garbled circuit that I generate will let you learn another key for every intermediate wires. But I have no idea if these keys are 0 keys, 1 keys, just one key for every wire until the end. And in the end, you're going to get some output key. And I'm going to tell you this output key is 1. This is the output that I want you to do. Yeah, this is easy to simulate. You don't need to know the input. You don't need to know anything to create this kind of thing. Okay, and this is all you see when you evaluate the circuit, so this simulation will be perfect. So let's do that. We're going to generate a garbled circuit, but instead of garbled gates, we're going to have simulated gates. Okay, we'll see how these looks like. They look similar to garbled gates, but they're not exactly the same. And we're going to choose two labels, two keys for every wire. But now we're not calling them the 0 key and the 1 key. We're calling them key star. This is the key that you're actually going to see when you evaluate the circuit. This is the active key. And there's also an inactive key that we call key bottom. Okay, so when you evaluate the circuit, you're going to see all the stars, none of the bottoms. Okay? So we have no idea if the star is the 0 key or the 1 key because we don't know the input, we don't know the intermediate wires. We're just creating these keys to kind of, you need to go through the motions. You need to evaluate something that looks like a garbled circuit. So these are the keys that you're going to encounter. So we're also giving you this fake output translation table that says the active key for the output wire gives you the correct output of the circuit. The other key is giving you the other value. So this is the only time that you actually learn one of the bottom keys. All the other bottom keys are just in our head. You're never actually going to see them in the construction. Okay? So let's see how the simulated. Okay. So to garble the input, obviously I'm going to give you one key for every input. Which key is it going to be? The active key. You're never supposed to see the bottom key. So I'm just giving you the star key for every one of the input wires. I don't need to know the input. It's just I just give you the star key. That's how I chose it. And this is how a simulated gate looks like. So this is the simulated gate, the first simulated gate. Remember, every gate looks a little different. So this is the first gate. The rows are in random order, but that doesn't matter. Of course, we need to permute the order because this is what's happening in the original construction. But the point is that if you get both active keys, if you get both stars, you get the active key for the output. But every other row that involves the bottom keys, remember, you never see the bottom keys, so you can never open any of these other rows. I don't know what you're supposed to get if you open them. That really depends if the bottom key is a 0 or bottom key is a 1. I don't know. I'm just going to put junk there. Okay? And I'm claiming that it doesn't matter what I put there, because you're never going to open these encryptions. These encryptions, you need at least one of the bottom keys to open them, and I never give you the bottom keys. So I can put here junk. I can put here maybe K7 star. Okay, I can put everything the same. So if I knew what is the correct value of K star and K bottom, if I knew how they match to 0 and 1, then I can actually put the right values here. I can actually complete these junks to the right output keys. That depends on the semantics of the wires. But I don't know, so I just put junk. That's okay. So to create this garbled, the simulated gate, I don't need to know anything about the input or the output. I can just generate it using the active keys and inactive keys, and I generate one of these garbled gates for every one of the wires. So now I'm going to prove to you that the simulation is good, and we're going to do this in steps. So first of all, we're going to show that one simulated gate, garbled gate, looks like an actual real garbled gate. And then we're going to argue that all of the simulated gates together look like all of the real gates together. So we're going to do it in steps. Okay, so So here's a zoom-in picture of the first simulated gate. Okay? So the simulator, given the output, produces a simulated input and a simulated gate. The simulated input starts with these active keys, 1 and 2, and it also has other active keys, but we don't care about them because we're only zoomed in on the first gate. So it only involves the 1 and 2 keys. So now, how does the simulated gate look like? It takes, it has an active key and an inactive key for every wire, and the table is exactly as we said. It contains one active row which contains both of the active keys and gives you the active key out, and all the other rows, they're just encryptions of junk. On the bottom here, we have the real gate. In the real gate, it's generated by the real encoding algorithm and the real input encoding algorithm. The input encoding gives you one of the labels depending on the input. So if the input is 0, 1, you get K10 and K21. And you also get other keys, which we don't care about because we're only looking at one gate. And then the key has this, the right semantics of a NAND gate. So if you look at 0, 0, you get key 1. If you look at 1, 1, you get key 0. So what is encrypted here under the double encryption actually matters. It actually depends on the semantics of what is 0 and what is 1. Okay, so to prove that those two things are indistinguishable, it's not even clear what it means now, I'm going to look at this hybrid experiment, okay, where I still work with the labels of the simulated gate. I still work with an active key and an inactive key. But now I kind of know the input. I know if the active key corresponds to 0 or the active key corresponds to 1. So this hybrid experiment knows the input. Unlike the simulation that has no idea what the input is, this hybrid experiment will depend on the input. So we have these two active keys in the input, and here we again have the active keys and inactive keys. But now, these double encryptions, they don't contain junk. They actually contain the correct output key, depending on the semantics. So here we think of the active key as being 0. Here we think of the active key as being 1. Which means that, for example, if we evaluate the gate on 1, 1, we're going to get a 0. So if we evaluate it on 1, 1 here corresponds to inactive, active. So inactive, active gives us the inactive output. The inactive output corresponds to 0. So 1, 1 is going to give us a 0. Okay, and you can do this experiment for every row and see that the semantics is really good. So what's the difference between the hybrid experiment and the real garbled gate? I claim that the only difference between these two guys is just renaming. I just took K10 and called it K1 star, and I just took K2 star and called it K21. I just assigned semantics for the keys. The active key is 1, the active key is 0. Other than that, everything looks the same. Okay, so there's really no difference between these hybrids. This is just like a mental hybrid that helps us understand what's going on. So the more interesting thing is what's going on between this hybrid experiment and the simulated gate. Why are these two indistinguishable? So the reason is that the only difference between these two guys is that what's encrypted under the double encryption is different. Here we have K7 is same in both, but here we have in all the inactive rows, we have junk here, and here we have the correct value. And the correct value actually depends on the semantics, so this is really the difference. So why are these two gates indistinguishable? They differ in what's inside the encryption. Why are they indistinguishable? What security property are you going to invoke in proving this indistinguishability?
Semantic security.
Right. So if the only difference is what's inside the encryption, then the proof is going to use semantic security.
You can have more hybrids by changing each of the...
Right. So I'm only highlighting here the important hybrids. But because you're actually changing more than one encryption, you're going to use more hybrids. In fact, you're going to use 3 hybrids. If you want to use more, that's fine. I don't know if you need to. But this is kind of the hybrid that I want to highlight. Okay, the intermediate hybrids are kind of derived from this big one. And why can you use semantic security? Why is it okay to change this encryption of bottom to this encryption of K7 star? Because this is encrypted under 2 encryptions, at least one of which you have no idea what the key is, right? At least one of which is an inactive key, and I never gave you the inactive key. I only gave you the active keys. Okay? So all the rows that are inactive, I can change what's inside the encryption by using semantic security. Is this point clear? So first we use semantic security to change what's inside the encryption, and we choose what to put inside the encryption by using the semantics of is the active key 1 or 0. And we can't do this in the simulation because in the simulation we don't know if the active key is 1 or 0. We don't know if the intermediate values of the evaluation. We only learn this. We only know this in the actual garble. So this is This is the argument that kind of looks at one gate. Now in the simulation, in the actual simulation, we have a lot of simulated gates, one for every wire. And we want to argue that you can kind of change these simulated gates to real garbled gates one by one. So the first strategy is to switch from simulated gates to real garbled gates one by one. You do this through a sequence of hybrid arguments. The number of hybrid arguments is really the number of gates in the circuit. One hybrid and maybe sub-hybrid for every one of these gates. So it sounds kind of straightforward and technical. You just go over the gates one by one. But it turns out that it's really important here the order in which you do these hybrids. So what do I mean by that? So you can start by changing this gate from simulated to real. All the other gates stay simulated. And then do this one, and so on. Another option is maybe start from the inputs. Start from this gate, change everything in the first layer, then change everything in the second layer. So does this matter? What's the right direction to work in? Does anybody want to guess? So this question of what direction to go for is kind of it's a hardcore question. If you can, it's a yes/no question, left or right. If you can guess the answer to this question with probability more than half, this actually means that you understand the entire construction perfectly. So as an exercise, after you review the construction, try and maybe forget the direction and try to guess it, maybe multiple times, see if you have. Okay, so let me tell you the answer. You're going to change it from outputs to inputs, okay? Don't take my word for it. Don't just remember, oh, you always change it from outputs to inputs. If I ask you, for example, I give you the garbled gates and I want you to change it to simulated gates, then you need to start from the inputs to the outputs because I asked you the opposite question. So the direction is not always from inputs to outputs. It really depends on the question that you're asking. Okay. So why from outputs to inputs? Why is this the right direction, by the way? We'll see. You just need to guess with like 5.1 program. Okay, we'll see. Why is this the direction? Let's see. So when you're changing the simulated gate from simulated to real, you're using semantic security, right? You're using the fact, so you have some row here that is encrypted under these keys, right? It's encrypted under, let's say, the inactive keys. And you want to say, it doesn't matter what's encrypted here. It could be junk or it could be the real key K12. Okay? And you want to use semantic security. What does it mean? It means that I give you an encryption of either K12 or junk under, let's say, this inactive key. And I want to say that you can distinguish the two. Let's say that you can distinguish the first hybrid where everything is simulated from a hybrid where the simulated gate is actually real garbled gates. If you can distinguish these two experiments, you can also distinguish the encryptions. How do you do that? You get the encryption of either K12 or junk. You build around it all this garbled circuit, and you try to distinguish between the garbled circuits. And if you can distinguish the circuits, you can distinguish the encryptions. Okay? The idea is that you get one encryption, and you build everything around it, and this is how your reduction works. Okay? If you've done some reduction in the homework, you already know this habit of getting one element, completing the entire object around it, then distinguishing the big object to deduce something about the small object. So if you want to build this reduction, you get one encryption, you build everything around it. Your reduction doesn't know if you're getting an encryption of K12 or junk. In particular, your encryption has no idea what these keys are, what these inactive keys are. If you can distinguish the encryptions under the inactive key using the inactive key, that's not very impressive. I want a reduction that doesn't know the inactive keys and it can distinguish. Okay? So building the rest of this garbled circuit around the encryption, this has to be done without any knowledge of the inactive keys. So do you need to know this k bottom, k11 bottom to complete this construction? Yes or no? The answer is no, because if you look at this simulated gate, for example, it never outputs the inactive keys. It just outputs the active keys or junk. Okay, this is where we use the fact that the simulated gate has no information about the inactive key. Okay? If it was a real gate, it actually has the inactive key inside of it. It's under the encryption. But again, if this wasn't simulated, this was a real garbled gate, it would have the inactive key. So we couldn't actually complete the reduction. We had to kind of complete the garbled circuit. It uses the inactive keys, but this is exactly what we're going to reduce to. We want to reduce the semantic security of this key. We're kind of stuck in a loop, you know? If we need to distinguish encryptions, we need the key. That's not good. But we're in luck, because the simulated gate only contains the active key. So that's the idea. You switch one gate from simulated to real garbled gate, but all the other gates before it are still simulated. So all the keys that are used in the semantic security argument are here appear nowhere previously. If you would try to do things in the other direction, you would totally get stuck. So you start by switching this from simulated to real. That's okay, because I never give you the inactive keys. Now you do maybe other gates. At some point, you'll need to switch this one. And when you want to switch this one, you'll have to simulate, you'll have to kind of build around the rest of the circuit, but you already changed this from simulated to real. So you have to build this real. And you don't know how to build this real because you're not allowed to have this inactive key. Okay? So that's the very long explanation to this very short answer. And again, I encourage you to try to recreate this by yourself. So just to sum up what we've seen today, we saw how to construct a two-party computation that is different than the GMW protocol from last week. It has only a constant number of rounds, but it actually tailored to two parties. It's not clear how to extend it beyond two parties. You're going to maybe explore this in the homework. And the ingredients of this construction were this new notion called the circuit garbling scheme that has a lot of applications on its own, and together with oblivious'Transfer, which is the same oblivious'Transfer you used last time in the GMW protocol. And in most of the lecture today, what we did is construct the circuit garbling scheme based on a secret key encryption or one-way function. So this construction kind of stands on its own. It has a lot of independent applications. But the first application of the circuit garbling idea was to a two-party computation. So just some exercises to make sure you understand this construction correctly. So first write down the simulator of the garbled circuit formally and prove that it's valid. In particular, answer this question of in which direction do I start changing the garbled gates from simulated to real? The second question that is interesting and will also be useful for you in the homework is to think about this encoding functions. So this one encodes the circuit, this one encodes the input, this one decodes the two garbled circuit, the garbled circuit and garbled input. I'm asking, what is the complexity of these functions? How hard it is to encode a circuit, how hard it is to encode an input as a function of the size of the circuit, for example. Specifically, I'm interested in the not the size complexity, not how much time it takes you, how deep is the circuit that implements this encoding. If you write this encoding down as a circuit, as a Boolean circuit, what's the complexity? What's the depth complexity? How many layers? And I want to bring this down as much as possible. So one thing that I want you to think about is there is some natural lower bound. So if you take if you're trying to garble a circuit that has a very large depth. So the circuit that you're trying to garble looks like this. It has many layers in it. Okay? Then I'm claiming that the depth complexity of the circuit encoding plus the depth complexity of the decoding has to be at least as much as the depth of the circuit. Why is that the case? Because computing the encoding of a circuit and then computing the decoding of the circuit, one after the other, is just an alternative way to evaluate the circuit, right? You encode the circuit, you encode the input, then you decode, you get the output. So you went from the input to the output. So if the depth complexity of these procedures together was significantly less than the depth complexity of the circuit, you could actually take any circuit and kind of compress it down. But this is something that complexity theory tells us we don't know how. So you have some lower bounds. You know, you have to, the sum of these procedures have to be at least as much as the original circuit. But actually, one of these procedures requires a high depth, and one of them can be implemented in a very shallow circuit. So figure out which one, and this will help you in the homework. And that's it. Thank you.